Hey guys, it's Professor Goodman. Um, Today for this video, I'm going to go through a few of the problems in the test review. Um, this is the first video in a two-part video series. The first part, I'm going to try going over really the first uh, close to half-ish of the semester. Um, so this will go through, the first part of the video will go through all of these. I want to hit on all of these subjects, which these are a pretty good summary of everything we've done in the semester. So I was hoping that, I actually looked at your guys' final, and I picked out some of the more important things that I saw. So this will be a very good tool for you guys when studying for your final. These will be most everything we've done in the semester, but I'm going to try focusing on a little more some of the problems that that might show up in the final. So some of these might show up in the final, some of them might not. But I will say that this is a pretty good um, it's a pretty good summary of what you guys will expect on the final. So for the first part of the video, I'm going to go through quartiles. So how we identify quartiles again. Remember, quartile is they're basically special percentiles. Quartile would be, first quartile would be the data value that separates your bottom 25% from your top 75%, right? So they're just those values. That's why they're called quartiles, because they go in quartile and go in quarters. And then, of course, the second quartile is also the median, and you know what the median is. It's the middle number, right? So we can calculate that pretty simply. And then your third quartile is, of course, the 75% mark. So focus on quartiles. Then I'm going to talk about regression. Remember, regression is how two variables relate to each other. So like when you're given a scatter plot, is there a good relationship? What does a positive relationship mean? A negative relationship, and so on. Conditional probability and some other probabilities, because probability is a tough concept to grasp. So I want to look at a problem or two from there. I think I'm looking at actually quite a few here. And then your mean and variance of probability distributions. This one just because there's that annoying should be actually more like standard deviation, but because there's this annoying part that we kind of have to talk about, that the sum product to find your mean, and then you have to do your sum product of x squared minus the square of the sum product of x, right? So that kind of annoying part. We'll go through that. Our binomial distribution. So it's been a while since we've done this guy, so we'll talk a little bit about him. We'll do at least a problem or two, and you guys should be good. The standard deviation rule, go over that, how to standardize and get a z-score on something, and then parameters, of course. So a parameter and a statistic. Remember, a parameter is a population data value. So like your population mean or your population standard deviation, that would be a parameter, right? And then the statistics are what you get from your sample. So you think population is parameter, sample are statistics, right? So we'll talk a little bit about that. And then lastly, for the first part of the video, or the first video, it'll be confidence intervals looking at one population. Okay, and then you can tune in. I'll have the other video posted also as well, and it'll be the second part of the final review. So I'll tell you what problem, or you'll see what problems I'm working with on the final review. So you should be able to pull it up on eMath and follow along. But hopefully this helps. This should be a pretty good tool for you guys when you are studying for your final. So without further ado, let's go. So first things first, I'm going to do the first problem just because I'm not going to focus too much on the chapter 1 or the test 1 material, because everyone did very well on that test. So I'm just going to kind of quickly go over it. But and also the same thing in the second video, I'm not going to talk too much about the chapter 17 stuff, because that's the stuff you guys just did, so I'll only do one problem from that. But my main focus is going to be the stuff that we had the most difficulty with. So test 3 and test 4 were pretty rough, so I'm going to try to do a few of those problems there weren't a ton of them on the non-credit test review. So I'm trying to evenly distribute everything. Although I'll probably talk a little more in depth as to why we do things in hypothesis testing and our confidence intervals. But for this first part, I'm going to try to just go through as quickly as possible. Okay, so question 1. So here we have a frequency distribution, right? So, or a histogram. They say for speeds in miles per hour of 55 cheetahs shown below, describe the overall shape of the distribution. So this part's pretty simple. So really the two main shapes that you'll see in these, like you either have uniform, you have normal distribution, right? Normal distribution is like you draw a bell, so like this would be an example of normal distribution. And then you also have, you can have skewed to the left, skewed to the right. Skewed to the left just means, you know, you have more values kind of pulling you down to the left. You have some outliers. And then to the right, you have some larger values kind of pulling your distribution out to the right when the main bulk of your distribution is on the left side, right? So here we go. So frequency distribution for speeds, doesn't matter. We just want to know what's the shape. Well, here it doesn't look like there's any shape, right? Like it's definitely not normal distribution. In fact, actually, it looks like almost they're all the same, and that's kind of the hint here, is they look approximately the same. Now, the best way to think of this kind of a distribution is think about a baseball team, okay? So, or some kind of a sports team. Typically, what do the sports team wear? What do they wear? Well, they all wear the exact same uniform. So it's a uniform distribution, right? They're all approximately the same. So this would be a uniform distribution. So that's the easiest way to think about it. Like a baseball team, they all wear the same uniform. A uniform distribution means they all look the same. Approximately, of course. Okay, so, geez, it took forever. So then that's that one. This one right here, like I already said, it's a normal distribution, right? Remember the way you tell a normal distribution? You have approximate symmetry, right? So like on this side, there's approximately something close to it on this side. You can draw kind of a bell curve here. Like it starts at a smaller value, goes up to a maximum, and then starts decreasing. So this is definitely normal distribution. Okay, so that one would be, I don't need to even look at to see if it's right, because it's easy. This one right here, look, it looks like the bulk of the distribution is right around here, right? This is where we have most of the frequencies. This just means that the number that's here appears the most, and then around it appears a lot as well. But look at this, and then we have some smaller values out here. Like they don't, I mean, the larger values, but they don't occur quite as frequently. So it looks almost like it could be normally distributed if we only look at it right here. What's going on? Well, it keeps pulling the data over this way, so we've got some outliers. So outliers on the right. So this would mean that it is right skewed, right? So right skewed just means, hey, we got some data values that are outliers, and they're pretty large values, so they're on the right. Okay, and then here, what do you guys think this is? Well, left skewed. Same thing. Okay, so now let's go to a quartiles problem. I just want to start with those. These you guys should be able to do. They are not that, this is not way too hard, right? You should be able to do all this stuff. You can figure this stuff out by yourself. This is really just like mean, median, and mode. That's pretty basic stuff. And then this shouldn't be too bad, just using your standard deviation, like equals STDEV and equals var and so on. So not too bad. Okay, here comes the first one. This one has to do with quartiles. Okay, so here it says, which of the box plots best resembles the box plot for this data set? So first thing I would do, copy over your data set. Let's copy this over to Excel. Okay, so this is my data set. So I need to find my quartiles, right? Because here they just give me these pictures, and I have to figure out which one is the best. So the easiest way to think about these quartiles, remember this right here, this bar is either your max value, or well, pretty much it's easy to think about it. It's just your max value, and this down here is kind of your minimum value, right? So and then the box is really the important part. The box here, this bottom one, this is your Q1, right? So your first quartile. Then this line in the middle is your second quartile, or the median. then this right here, the third one, of course, is your third quartile, and then this is your maximum value. That's how box plots go. So let's find these guys. So the way you look for quartiles, remember, is equals quartile. Now don't do dot exclusive, dot inclusive, just do quartile. It's the easiest one. Then select all of your data. So this is kind of annoying. I hope it doesn't count these as zeros, but let's see. So my quartile then is, I want the first one, so I put 1 there for the first quartile. So the first one they say is 18. So let me just make sure that that it doesn't count those blank spaces. I don't think it will, but just in case. So I highlight all this, comma, or all this. Will that work? No, doesn't like me doing this. I would think that this would work, but I guess I could just do this. Do 63, so there's 63, 67, and 75, and I'll just kill this. Okay, now I need to fix this. So let's see if it's still that same value. Just making sure. I'm pretty sure it will be, but you never know. First quartile. Okay, yeah, so it thankfully does not count the blank spaces. So you don't have to worry about that. So it's still 18. So this is my first quartile, so Q1, which I like putting on this side, but whatever, I'll just do it in this one for this example. Now I need my Q2, which is also the median, and then I need my Q3, right? And then you can also do your min and your max, just, you know, that might help in case there's something, but I think really just your Q1, Q2, and Q3 is good enough. Your Q2 you can find either by doing quartile with a 2, or the easiest thing is just to realize it's median, right? So if it's median, then just do equals median. Okay, so 25, now my quartile for the third one. Okay, so let's highlight all of this junk here. And then 3. Oops, I accidentally put an extra set of parentheses there. There we go. And then, of course, you can do your max value. So max, all of these guys should be 75, I think. Yeah, and then your min. So my min value. Okay, so my minimum value. So here we go. So this is my 5-number summary, as they call it. So let's check to see if anything matches up with that. Okay, so these are my 5-number summary. So my smallest number is 7, so it looks like they all have the right min. It looks like they all have the same max as well, so min and max in this problem is not going to help us. We've got to look at our Q1, Q2, and Q3. So Q1 here is 18, so look for something that looks like it starts on 18, so something that's approximately close to 20. A looks pretty good, right? B is definitely, well, I mean, I don't know, it looks more like it's closer to 15 or 16, but we'll leave that one there for now. So maybe A and B are possible answers. I'm leaning more towards A. C is above 20, right? So definitely not C and definitely not D. So C and D, kill them right away. It's either between A and B, and I'm leaning towards A, right? Because this bottom here, which is the Q1, it looks like it's closer to 18 than B is. B looks like it's closer to 15 or 16, but it's too close for us to tell right away. But look at the big difference between medians. So we'll have to see. Which one is correct here. Okay, so this median is 50 about, and the median is definitely not 50, right? This median is only 25. So right away, you know which one's right. It's A. So you type in A. And you check your answer, and the green thing of "you're right" comes up. And there we go. Okay. Whoa, that's kind of weird. Using data set, what's the range it gives us? Oh, 95 confidence interval for the mean of their purchasers. Okay, that's kind of weird. I don't know why they'd have a confidence interval problem here. Why would they have it here? Well, for whatever reason they have one here. I don't know why, but yeah, well, I'm not doing confidence intervals until the next problem. So when you're going to answer this part for part 2, just come back to this one. I'm not sure why this one's here, but when I go over confidence intervals, well, I guess I go over it at the end. I don't think this should be here, but whatever. We'll go ahead and answer it, I guess. All right. So first things first, we need I have my mean, right? And I need, what else do I need? I need my sample standard deviation. In fact, I don't even think you guys have you guys even done a confidence interval with t? Whatever. Well, here we go. So sample standard deviation. Also need that special z-score, and because well, the confidence level they say is 95%, so 0.95. Either you have that z-score memorized, because I don't think it gives it to you. No, it doesn't. So we'll have to find it. So we need that special z-score. Then we find our margin of error, m, right? So this is our margin of error. A little earlier than I wanted to do this problem, but whatever. Okay, and then with that we find our lower and our upper, right? Oh, we also need to have our alpha. So sorry about that. Let's insert here and have alpha. So alpha, remember, is simply 1 minus your confidence level. So not 1 equals 1 minus confidence level, so 0.05. The z-score then would just be it's a, well, let's look. So let's look back at this problem. How many of these do we have? I don't know how many ages we have, so we got to count this. So let's see. We have 33. Okay, so we have approximate normal distribution, but why is this not a z, or why can't we use a normal distribution? They don't give us our population standard deviation, right? And that's really the only thing you have to check, because most times they'll give you the right amount of n, so the only thing really you have to check is standard deviation. Okay, so they don't give us a standard deviation, so that means I cannot do a z, it has to be a t, right? Does that make sense? So that's kind of the only thing you check whether or not you're doing z or t is check standard deviation. If the population standard deviation is given, it's z. If it's not, it's t. So for here, we have to do t dot inverse. Okay, now the probability, remember that's your 1 minus alpha divided by 2. Okay, and then I think, oh, they ask for the degrees of freedom in this case. The degrees of freedom, remember, is always your n minus 1. It said we had 33, so it would just be your 33 minus 1, which is 32. Okay, so this would be the t, and I think that's what they got too, right? Let's check. About 2. Yeah, they got the same thing. Okay, so let's get these values here. So my mean then is man, yeah, this is weird. I don't know if you guys have had a problem like this even in your homework. Well, at the very least, you know, if you're watching this video or you're doing this test review, you see this problem, and if it does pop up on the exam, you would know how to do it. But since this is a t, we need our standard error, right? So once we find our sample standard deviation, we use that to find our sample error, or standard error. Okay, so our mean is easy. It's just equals average. So we take our average of all of these values here. So we do this, highlight all these guys, and that is our mean. Our standard deviation is also simple. It's easiest way to remember it is STD, and then it's comes up. Now it's not the population standard deviation because there's probably more than 33 values. So let's go with .s. That means sample. Okay, highlight all this junk, and we got our sample standard deviation as well. Okay, now our standard error. Your standard error is crap. I probably need to actually put my n here too. Jeez, you can tell I was not expecting this problem. It's just kind of a mess. But this is what you need: your mean, sample standard deviation, your n, standard error, then you have your confidence level alpha, your t-score, then we can find our margin of error, right? So thankfully you don't have to memorize how to find your margin of error formula. It'll be given. All right, but here we go. So n was 33. My standard error then is my sample standard deviation divided by the square root of n, right? That's how we find my standard error for a t-test or a t-score problem. In this case, a t-interval. So here's my standard error. Good, so 3.09 or whatever. Now I can find my m. So my m is simply, okay, take your t times your standard error, right? And there you go, 6.29. So my lower is going to be my mean minus the 6.29, right? And then my upper is my mean plus my margin of error. Okay, right? That's what it is, just x bar. So this should be x bar. X bar minus m, x bar plus m. Okay, so there we go. And that should be correct. Let me double make sure. I was not expecting this. So 23.7, 36.3. Yeah. Okay, cool. I hope that's not what it gives you, that part. But you know, if in case they do, you have it now. All right, so cool. So this guy is done. Let's go on to the next problem. So that's 8. Let's go to problem 11. So this is the regression problem. Okay, so scatter plot here. We have a scatter plot, and they give us our data here, and then they say find the slope of the least squares regression line B. Okay, now here this would help. Remember that you guys have the formula, so you don't have to even worry about doing this. Oh, okay, there we go. You guys don't even have to really worry about you know, finding your R. You don't have to type in all these values and find your R. They give it to you. But your formula for your B, remember B is equal to your R times your standard deviation of Y. So your standard deviation of Y divided by standard deviation of X. Okay, and that is your B, or your slope, as they call it. This is your slope. Not sloper, it's your slope. Okay, so let's find this guy. So my B is simply going to be my R, which the R they give is 0.984. So it's equals 0.984 times my standard deviation. So my standard deviation for X is the age, because they say here, look, if you have trouble figuring out, well, which one's X and which one's Y, your Y is up down, right, and your X is left right. So age is your X, Y is your time. Okay, so that should be pretty simple. So 14.07 is your X, so that's what you're going to be dividing by, and then 24.26 is your 24.26 is the oops, crap. No, stop. 24.26 is your standard deviation of Y. Standard deviation of X is your 14.07. So 14.07. Okay, so then this would be your B, right? So good. So now you find our B. Now the other thing we had to find, so we throw that in there. Make sure you follow these directions. You will get some points off, or even the entire thing wrong, if you do not put this in the correct form. Don't look at the number they give you. If they say like this, sometimes that can be misleading. Make sure you do this. If they tell you round to the nearest hundredth, what does that mean? Well, that means to 2 decimal places, so it'd be 1.7. So make sure you do that. Okay, and then, oh, I hate this. So make sure you have your rounded solution, 1.7, because that's what we put in here. Make sure 1.70. Check your answer. Hopefully it's right, because there have been a lot of issues with this guy. And then they say, if you are using Excel, use the rounded slope from the previous part for your calculations. So yay, use your 1.7. So make sure you're doing this for your A. Now what's the formula for A? Well, A is equal to my, it's the y-intercept, so it's going to be your y bar minus B times x bar. So what is my x bar and y bar? Remember, those are just my means. Y is my mean of the time, so your up-down mean, and then x bar is your mean of age, so your left-right mean. Okay, so let's find it. So my, oh, no, don't do that. Oh, it's like Excel tries to think for you, and it just doesn't work out. Okay, so I need to get back to my means and so on. So mean of age, 35.9. That's my x. My y is 243. So what I do is I take my b from my last part. So I have my, well, my y bar is 243.3. So 243.3. And then it is minus my b times my x. So my x bar, my x bar is the mean age, so 35.9. So 35.9, and there we go. My A is 182.27. Now I hope that this is correct, because for some weird reason we had a lot of trouble with these guys in the past. Now it's rounded to the nearest hundredth, so this is the nearest hundredth. Please say it's correct. Okay, it is. So make sure you read the instructions when you're doing these problems. I know I don't do it sometimes, so don't follow my example. But in this case, I did it right. So follow this example to the T. You know, like the t-test. Ha ha ha. All right. So which of the following is the correct interpretation of the slope of the least squares regression line? All right. Now be very careful about what the question's asking here. They're asking for the slope. So remember, your slope is defined to be the rate of change in your algebra class, right? It's the value. It's the value of y. Like, how does your y change with each unit increase of x? So as your x goes up, what's happening to y? This is what it's saying. So our formula is going to be y is equal to a plus bx. I think that's how they do it. So this is approximately your line, right? The b is your slope, so it goes with the x. Your a is the y-intercept, so it stays on the outside. Doesn't have an x attached to it. So this is my formula, right? So it's y is equal to my a, which is 182.27, plus my b, which is 1.7 times x. So look at this. So this is what it's asking. All right, so it's asking, how does my slope change my y? Well, look, if I put x equals 1, my y goes up by 1.7. If x equals 2, my y goes up by 1.7 times 2, right? So 3.4. So in other words, for each increase in x, so each increase in x, my y variable goes up by the slope, so by 1.7. So that's what we're going to say. Which of the following is the correct interpretation of the slope of the least squares regression line? So don't do the every 1.35 years, or every 1.72 years, or every 1.7 years, because that doesn't make any sense. It's every 1 year it goes up by 1.7, right? So every year a runner's age increases, his finish time is likely to increase by 1.7 minutes, right? Because 182.27 is the base number, right? That's the y-intercept. So when x is 0, y is 182.27. But every time that x goes up, so the age of whoever's running goes up by 1 year, this gets added to that amount of time. So it goes up by 1.7. So each year a runner's age increases, his finishing time is likely to increase by 1.7 minutes. That's what this means. Don't do any of these right away. Every 1.35 years, every 1.72 years, every 1.7 years. Those are nonsense answers. Don't use them. It should be either this guy or this guy, and this guy's total increases by 1.35. Well, that's just incorrect, because the slope is not 1.35, so this guy is the clear answer. Okay, so use least to predict for a 21-year-old male runner. Okay, so now we're just going to use this guy here. So if he's 21 years old, that's his x, right? So then this would mean for 21-year-old, we have y, so his time is 182.27 plus 1.7 times how old he is, right? Because remember, x is the age. So it should be 217.97. So let's see. Hopefully, again, this works, because it's been acting very strange for these problems. But 217, so 217.97. Okay, hopefully we did everything correctly. I'm really hoping. Yeah, we did. Okay, cool. So that's how we do the regression part. All right, so let's keep going. 2, conditional probability. So we're going to 20. So we finished up that problem. Now, so we did this guy, right? So I'll bold them as I go through, I guess. Maybe if I can remember. Conditional probability. Now is the next part. So we're doing conditional. After I kill all this, because I don't want to look at it anymore. All right. Conditional probability, so problem 20. So I entered 20. Okay. So this isn't a conditional probability, but it's probability, so a good introduction. Okay, so results of players in the U.S. Open tennis tournament are displayed in the table by gender. If one of the challenges is randomly selected, find the probability of getting a challenge with a female player. So if one of the challenges is randomly selected, find the probability of getting a challenge with a female player. Okay, so here's my, so actually first let's copy this guy over. Hopefully he copies over well. Sometimes they, have some issues. Whoa, right now my Excel is having issues. Why are you not responding, Excel? Okay, for some reason my Excel wanted to just not work. Okay, so I guess we have to kind of do this in our heads. What the heck? We can't do this in our heads. It's impossible. Ugh. It sucks because the sheet isn't, the sheet that I had was there. I don't understand why it's doing this. Why? So just bear with me, guys. So, because I'm not going to stop the video just because it'd be annoying. So just skip through this while my Excel decides to not work. I've never experienced this before. This is terrible. Let's see, is it this? How do I? Can't remember how I do the task manager on a Mac. Can't remember. There's a key for it, but I'm not sure. Like, what in the world? Why is it doing this? I didn't even click anything. I just copied this junk. I didn't even paste it yet. Jeez, what the heck? Okay, there we go. Oh my gosh. What the heck? Alright, well that sucks. My parts are gone now. Alright, well, whatever. So here we go. I have it written down, so we should be okay. Alright, so let's do this. So I copied over this. Now I'm going to paste. Alright, so because it gives you that blank spot here, it never copies over, so just always push them over here, like that. And copy it, take it one over. Okay, so here, what are we doing? We're saying if one of the challenges is randomly selected, so one of the challenges, find the probability of getting a challenge with a female player. So it doesn't, if one of the challenges is randomly selected, it doesn't tell you whether or not the challenge was rejected or not, right? It just says if one of the challenges is randomly selected. So you have to do, it's the total, so all of your challenges are selected, so the 839, and then the probability of getting a female player. So a female player is this, right? So the 350. So probability getting female is pretty much all we have to do. There's no conditional probability in this one because it just says a challenge is selected. So that means either the challenge was accepted or rejected. So either way, so it's kind of tricky. But here's a female player. We have 350 females, and then divided by the total. So about 42-ish%. So let's see how many decimals we need to do this to. It says that we want 4 places. Okay, so I need to show you guys this too. Be wary when you guys are doing this. Like when you are using this to change the format of the cell, be careful. The cell will remember that. So if you are trying to do further questions, so like if you use this cell and you're like, yes, and you throw it in there, you throw this in here and you're like, yay, hopefully this is right. But you throw it in there and it's correct and you're like, yay, okay, that's perfect. And then you delete the problem, So if you delete the problem, so I delete this guy, look what happens. Okay, I get a solution. So if I get my solution is 0.2314583. I'm just making a whole bunch of random numbers. You get this. Look what it did. It still remembers the format of only being to 4 places. So if you have a problem and you're using this cell and it only gives you 4 places, that could be the solution. It could be that all after that is zeros. But if it does, but you have to be careful, because if the problem that you're doing currently, so not this one but a later one, the problem that you're doing, if it says round to 5 places, make sure that it doesn't actually have 5 places. So see, like I go back up here and I click on this cell, look at that. I would get that wrong. I would get that problem wrong because I would only put 4 in there rather than 5. So make sure, be very careful when you guys are doing these problems to check that. Okay, so if it says 5 places, make darn sure that it's 5 places, because it might be that your answer is this, 2, 3, 4, 5, right? Then you're okay. But just in case, still go over here and increase the decimal. Oh, look, see all the zeros. That means that 5 is the last number that actually has a number. But as before, if you have this and you increase it, look, there's another number hiding back there. Okay, so just be careful about that. So definitely want to make sure you guys get the maximum amount of points that you can possibly get. Okay, so cool. So that's my that's one of the problems. Now we'll go to problem 24. So problem 24. This one's easy. So here is a probability distribution table. We have to find the missing probability. So this is, you just have to know what this is. Okay, so my probabilities here. So the probability of a thunderstorm is 22%, light rain 20%, partly cloudy 44%. What does that leave for sunny? Well, remember, this guy here, this has to sum to 1, right? This has to sum to 1. If it does not sum to 1, then it is not a probability distribution. So this is the easiest thing to do. You have to think about it in terms of complements. So if you have 22% chance for rain, thunderstorms, 20% chance for rain, and 44 for partly cloudy, sum these guys up, the sunny is going to be 1 minus the sum of these guys, right? It's whatever's left, because either it's going to be thunderstorming, light rain, partly cloudy, or sunny. It's not going to be anything else. So it'll be your full 100% minus the probability of the other guys happening. And there you go. Sunny is 0.14. So you would throw that in here, 0.14. So make sure you actually put it in there too. If you don't, then it'll freak out. So that's where you put your answer. You have to type it in. Okay? And then 25. So for 25, this is OR. So I'm not even doing a conditional probability problem, or I don't have one here. I'll do 28 in a second. But here's 4. So this is the rules. I say 25. So this is a rule. So remember, in probability, be very careful to check like what happens when events are independent or if they are mutually exclusive. So if the events are independent, or if they are mutually exclusive, I think they call that something else. I think, oh, disjoint, that's it. They call it disjoint too. I think in this class, when I was learning it, they called it mutually exclusive, but in your class they call it disjoint. So make sure I don't confuse you guys. It's just disjoint. Okay, so we have, if you have independent probability of A and B, right? So their intersection is equal to probability of A times probability of B. Be very careful that you get that right. If they are independent, it does not mean that their intersection is 0. It means that they have this, the probability of A times B. So the probability of A and B is probability of A times probability of B. It also is this, probability of A, or probability of B given A is simply equal to the probability of B. So they're independent. Their probabilities do not influence each other. Then disjoint is the probability of A or B is simply equal to the probability of A plus the probability of B. This just means that the probability of A and B for this guy, so probability of A and B is 0. Okay, so that's what it means to be independent and disjoint. So remember that. That will be fairly important. I imagine there will be at least one problem that deals with this. So if it says, "Hey, find this probability," and it's I don't know, like a union problem. So it's like find the probability of A or B, and it says, hey, they're independent. It's not this. If you have independence, it does not mean that there is no intersection. It means the intersection is found through this product. So you have to do this, then do this next part. I think there's that problem actually right here. We'll do it in just a second. Okay? So here we go, at Dee Dee's Donuts. So if you like Dexter's Laboratory, this is Dee Dee, what she did with her life. She built a donut shop. So at Dee Dee's Donuts, the probability that a customer orders a donut is 0.71. The probability that a customer orders a cup of coffee is 0.3. And the probability that a customer orders both a donut and a cup of coffee is 0.2. What is the probability that a customer orders a donut or a cup of coffee? Ah, okay. So here we have the probability that coffee or donut, right? This is what we want. So now remember the probability, so probability of A or B is equal to the probability of A plus the probability of B. Now if they were disjoint, that would be it, right? But it doesn't tell us that they're disjoint, so we have to assume that they are not. So probability, you have to subtract the probability of A and B. Okay, so that is what we need to do. This is the formula we need to use. So they give us all of the information that we need, right? So I'm throwing this down here. So they give us the probability of A, they give us the probability of B, and they give us the probability of A and B, right, in the problem. So, gotta change this. Coffee, right? Probability of coffee, probability of donut, probability of coffee and donut. And donut. I could actually use a coffee and a donut right now. That would be lovely. So if any of you guys want to bring, me a coffee and a donut on Thursday for extra credit, you know, no, I'm just kidding. I'm not allowed to give extra credit, and also that would be kind of mean. You guys aren't supposed to spend money for extra credit. So disregard I said that. It was definitely 100% a joke. All right, so my coffee tells me the probability for coffee is 71%. So 0.71. Then customer ordering a cup of coffee, 0.3%. And actually, I mixed those guys up. This is 0.71. Sorry, I should have put donut first and coffee because that's what they did. Now they said and they do both of them, so 0.2, 20%. So see, look at that. Because I'm using the cell, look, it's automatically showing me that much. So be careful when you see that. So the probability of coffee or donut is simply you take your coffee plus the donut minus coffee and donut. And there we go, about 81%. So 0.81. And they even want it, well, this time they tell you to look at this and they say just do not, they just say don't round. So we're not rounding. Throw it in as is. And there we go. Okay, so now here, this is a tricky one too. So we'll do 26 quickly. This is tricky. It's trying to trick you. If A and B are independent events, where this is this and this is that, find the probability of A or B. So this means you're still going to use this formula, right? You're still using this guy. But what's the difference? It says it's independent. That does not mean disjoint, right? So that means that the probability of A and B is not 0. It's going to be, probability of A and B is the product between A and B. So if we have our A, we have probability of B, then we need probability of A and B. Okay? So now, since independent, probability of A and B is simply equal to probability of A times probability of B. Right? There we go. So probability of A, they give me, is 0.2, and then B is 0.7. So we have 0.2 for A, 0.7 for B. And their product is simply, hey, take your A times your B, and you got it. So 14%. Okay? So then the probability of A or B, so probability of A or B, following the formula above, you take your A plus your B minus the intersection between the two, and you get 0.76. So 0.76. That would be my solution. And there we go, it is correct. So be very careful that you make sure that you know how to find the intersection. If it's independent, that does not mean their intersection is 0. It means that the intersection is found through the multiplication rule. So the just probability of A times probability of B. All right. So let's do finally a conditional probability problem, and then we'll hop on to our next part, which is the mean and variance of probability distributions. So here we go. Look at this. Probability that a randomly chosen female is getting her first license. So in other words, we are given what about this randomly chosen person? Well, we are given her gender, right? So we are given that this person is female, but we don't know what's the probability that this female is getting her first license. Okay, so let's grab all of our information over here. In fact, actually, I'm going to get a new one because I don't like how this is formatted here. Yeah, it's better because I don't like that some of my cells have that, and it just kind of annoys me that it has that stuff. I mean, I can go in and change them, but I don't remember what cells they were. Okay, so let's copy all this junk over here. So my previous license and all the way through. Make sure you're using Chrome if you want to copy over correctly. I mean, it might work on other ones, but when I was using Safari, it would never work. Oops, so I didn't copy it. Okay, now I did. Okay, so then I got to copy this over because that first space, for some weird reason, always is blank. So I will always do that. Okay, so here we go. So we're given that it's female, right, already. So this is what we're dealing with here. So the females. We're not dealing with anybody else. We're not dealing with any males. We throw the males away. Now we want the probability what? We're saying, probability a randomly chosen female is getting her first license. So we look then at first license. So let's do orange. So now what's the intersection? Well, whatever orange and this make, because it definitely makes blue. Okay, so here, what is the intersection between these two? Well, right here. This is your numerator. So remember, the probability of A or B given A is equal to the probability of B, probability of A and B divided by the probability of what is given. It's the probability of A, right? So this is what we're going to use. So first things first, we need our probability. So probability of A and B. Then we need probability of just A. Okay, so remember A, probability of A is the fact that she is a female. So probability that is given, we're given a female, so what is the probability she is both a female and first license? That is what we're looking for, right? Okay, so well then this is easy. It's simply her first female and first license is the intersection, so it's just this guy. And then female is, well, how many females are there? 20,000 approximately. Alright, so then here we go. So probability of A and B is this divided by the probability of A, so female. And there we go, about 28.64%. And tell me, is it going to give us an or reduced fraction? Oh, I hate that. Okay, so this is actually a good little learning opportunity, I guess, or if we remember it. Okay, so if we want to find a reduced fraction, because you can change the format to a fraction, so just right-click it, go to Format Cell, make it a fraction, right? Fraction, but it only gives you up to 3 digits, so that might not be correct. So go down to Special, or no, sorry, Custom. So you go to Custom, and you see this right here where it shows the hashtag question mark divided by question mark. Just click on either one of these, and then in here when it says type, right in here you can type how many digits you want. So make sure to just put a whole bunch of digits in there, and look at that. We get 1917 divided by 6692. So see, a lot easier than doing a prime factorization for your numerator and denominator and then eliminating common factors, right? A lot easier. So make sure you do this. So there we go. That is my answer. So I'll copy it. and then I'll throw it over here, and this should be correct. Make sure you delete all these spaces, because I don't know if it will like that or not. And there we go. It is correct. All right, what is the probability? Oh, geez, I didn't realize there were 3 parts to this. What is the probability a randomly chosen male is renewing his license? Renewing license now. Okay, so now this changes, right? So I'm going to leave this here, because if I leave this and I just change these numbers, the probabilities will change along with it. Okay, so now I want probability of male, because we're oh wait, no, I did A and B here. So male and renewing license. So male and renewing, and then we have probability of male, because he's given. All right, so how many males do we have? So let's unfill this. Unfill this. Go to no fill, so that way the bars come back. Okay, so then here, probability a randomly chosen male is renewing his license. So how many males do we have? Well, we have this many. So this is my number of males. And then renewing license. Renewing license means they had a previous license, right? So then they are in the previous license category. So be very careful about that to know when you can do that or not. So this is my intersection. Just always put a different color for there. Okay, so my male and renewing license is the intersection, right? So just hit equals, click on the previous license and male. Okay, then I do probability of male. How many males are there? 16,000. And there we go. This one doesn't look like it reduces at all. So we are good here. Okay, so just copy this guy over. Throw him in here. And make sure you delete any extra spaces just in case. But if you're deleting extra spaces, don't delete any of the numbers. Check answer, and it should be the green of happiness. What is the probability that a randomly selected citizen is female given they had a previously held license? Okay. So now change it slightly. So let's do no fill here, no fill, no fill. And this is actually pretty good because there's only really one of these problems. So this will help us out a little bit. All right, so now I want probability that a randomly selected citizen is female given they had a previously held license. So in other words, we have the probability female, or sorry, is it renewing license? Yeah, previous license. So previous or renewing, in other words, I guess, and female. Whoa, bad typing. So we have probability previous and female. And then the probability that we have previous, I believe, was what was given. Right, so probability given they had a previous license. Okay, so we have, let's do the same thing we were doing before. So we're looking at previous, so that means they held the previous license, so highlight that if you need to. Now, if you're really good at this, you don't have to do highlighting, but I'm doing it because it might help you guys see the intersection a little better. Okay, so green now this time. I don't know why I'm using all these different colors, but we see the intersection is between previous license and female, so it's this here, this middle part. So this will give him blue. Okay, so this is the intersection. So it's my intersection here. And then previous, well, there were this many previous. All right, and then that's your probability. So hopefully this is correct. Oh, make sure you delete any empty spaces. Now, it might still count it as right if you have empty spaces, but you never know. And there we go. That's how you do the conditional probability. Okay? So let's go on now. We're going to the next part, which is the mean and variance. So our mean and variance. So let's find these guys. I'm gonna try to speed it up a little too, just so you guys have, you know, this video isn't 3 years long, because it's kind of long already. And I don't want it to be way too long. So let's do this, okay? So let's copy over this. So we're trying to find our mean. So we need our mean here. And here we go. So if we need our mean in a probability distribution, there's a special way to find that as well. So first things first, let's make sure you say match destination formatting, so then the weird guys go away. So this is x, and this is probability of x. If you forget, you can go back and look at the problem. Make sure there's a probability distribution. These guys should all sum up to approximately 1. Yes, they sum up to 1 right here. So cool. All right. So now our mean, so my x bar, or I guess I can just do mean, because this could be population, potentially, but let's do mean. The mean is easy for a probability distribution. It's just sum product. So your sum product, highlight all of your x's, oops, not everything, highlight all of your x's, comma, highlight all of your probabilities of x. And there you go. Your mean is this. So that would be what I would throw in there. So I'd copy this, and I would toss it in here. It says to the nearest hundredth, so that would just be 4.46. Okay. Now they ask for the variance. This is the annoying part. So sometimes they'll skip the variance and go right to standard deviation. So please make sure you read the question, because if they skip right to standard deviation, you have to square root what you found for the variance, right? So here is my variance. So actually it's just a good idea to find all three of them. Unless they stop at variance, I guess. So my standard deviation. My variance, this guy is tricky. Okay, so watch carefully. I'm doing sum product just like before, but it's the sum product of x squared minus the square of the sum product of x. So that's an easy way to think about it. So sum product of x squared, right? P of x minus sum product of x, P of x squared. Right, so it's just that. But this guy here is our sum product of x, P of x. So all you really do is square him and you're okay. Okay, so my variance. So here we go. So the easy way to do this, sum product, instead of doing the x squared part, just highlight x twice. Highlight x once, highlight x again. Now highlight your P of x. And voila, there you go. So now, oops, there we go. Okay. Okay, so that's the first part. So now you need to do the next part. So we have the sum product here. So this is my x squared. This is the first part of the formula. Now I need the second part. So either you can type this out, or you can click on your mean. Oh crap. Well, unless they don't like it. So and then minus this guy squared. And there you go. That is your variance. So copy him over. Throw him in here. We went to the nearest hundredth. So that would be just the 0.95. Okay, hopefully this is correct. I feel like I say it for every problem. I think it's just because it really stresses me out when I see that red part. So I can kind of understand how you guys feel. So it makes me feel happy when I see the green. Now I need the standard deviation. Well, you would have to do the whole process again and take the square root, though. Unless you remembered this really, really nice relationship. Remember, the standard deviation is equal to the square root of the variance. So if you know this relationship, so this is equal to, sorry, square root of r. If you remember this, then this part's easy, right? You just go equals square root, click on your variance, and there you go. So we go over here, throw it in here. He's also to the nearest hundredth, which is just 0.82. Okay, and there we go. Cool. So we're just making our way along. So that's the only thing I'm going to do for that one. Now let's go into the distributions. So my binomial distribution, problem 34. So just right here, actually. Okay. So for a binomial distribution, remember, this is a discrete probability distribution, which means that your cumulative at the end, when you're doing binom.dist, it can be 0 or 1. 0 for exact, 1 if you're doing cumulative, which means up to a number. So here we go. So my n. So it says probability of having identical twins is 1 in 285. Choose 3,000 fertile women at random. Okay, so just go and find your fertile women somewhere, and then the probability of having an identical twin, for whatever reason, is 1 out of 285. So my n is the 3,000 women, right? That's how many people I'm studying. My p, that is just the probability. So 1 out of 285. It says enter p as a fraction. So 1 divided by 285. Okay? And that's all the magic for that part. So that should be a gimme right there. So easy part. Then here comes the harder part. What is the probability of having at most 5? So it's probability that at most 5 of these women. Oh my gosh, I'm active. What? Oh geez, all the way down to problem 33. Okay. Well, I mean, I guess I could just do it in that format, but page size, all questions. I'd rather it be. Let's see, I can just go to 33, I guess. Okay. It's page size. Oh, I see. It's doing 33 per one. Let's see. If I do 1, holy crap! No, definitely not. Let's do 10. Okay. Page size. Oh, because each one has its own thing. I'll just do 20 then, I guess. Okay, so let's go all the way down. No, never mind. I don't like this. I like all questions. This one's way too long. 91 questions is way too long to do that for. Okay, so let's go down to question 33. 34, sorry. Okay, so I got my N and P. Now I need to find the probability. So now this is when you're going to hop on over to Excel. So my N and I have my P. My N was the 3,000 fertile women, and then this is P is 1 divided by 285, right? All right, so there we go. So now the probability that X is at most 5, right? So less than or equal to 5. It's binom, so equals binom dot dist. And you do your number of successes. The number of successes I want, that's this guy, 5, comma, the number of trials, that's 3,000, there are 3,000 women. The probability of success is P, and whether or not it is cumulative. In this case, it is cumulative. The reason it is cumulative is because we are finding area up to a number. If we were finding this, the probability X is exactly 5, then it would look like this. Equals binom dot dist. Your number of successes, it's 5 still. Your number of trials is N. And probability of success is still P. But cumulative would be 0. So if you're trying to find exactly 5, it's always going to be 0 for cumulative. If it's up to 5, so less than or equal to 5, you mean you're summing your cases, then it is 1. Okay? And this is our solution. So go over here, and we want it to the nearest thousandth, right? So that would be 3 places. So 1, 2, 3. So 0.49. Or 0.049, sorry. And there you go. That's how you do that problem. So not too hard, right? All right, so now standard deviation rule. You can kind of cheat with this one. You don't have to use standard deviation rule, but we'll do standard deviation rule, then I'll show you. All right, so here. Probability of the randomly chosen male is between 66 and 72 inches tall. Use 68, 95, 99.7 rule. So probability between these guys. So let's see. How many standard deviations up and down do I go? Well, the mean is, oh, geez, the mean's hard to see. The mean is 69, right? So if the mean is 69, and my standard deviation, what the heck? Oh, geez. Okay, I was like, I don't know. All right, so here we go. They give you the stuff. The mean is 69, and standard deviation is 3, right? So that means if I go up by 3, that's 1 standard deviation up, or go down by 3 is 1 standard deviation down. So look at this. So 69 is my mean, and I'm going 66 and 72 inches tall. Well, how many standard deviations does it take? How many do I have to add to 69 to get to 72? Well, just 1, right? Because 69 plus 3 is 72. So that's 1 standard deviation up. And then 69 minus 3 is 66. So it's 1 standard deviation up, 1 standard deviation down. In other words, that is within 1 standard deviation. So since it's 1 standard deviation, it's 68, right? Because the 68, 95, 99.7, this is within 1 ST dev, within 2 ST dev, within 3 ST dev. So like, remember, the easiest way is when they show you this, they'll always show you this. The first number they give you is 1 standard deviation. Second number is 2 standard deviation. Third number is 3 standard deviation. So there's a direct correlation between the number of standard deviations your probability is and its rank, or its number in the sequence, I guess. Okay, so there we go. So probability that we have this. Well, it's within one standard deviation. So by this rule, it is 0.68, right? 68%. Okay. So within that one, these are pretty easy, but you might have to use help a little bit with your technology with this one if you want to. But let's see. So now we want probability chosen male is greater than 72 inches tall. So in other words, we want it greater than starting at one standard deviation and going up, right? So what I would do is I would take the whole. So the whole thing should be 100%, right? So 1 minus the within one standard deviation. This gets you the two tails. So within two of the tails, so one standard deviation, the probability of the standard deviation being above 72 and then below the one standard deviation below, this is both of those probabilities. So if you divide this by 2, then you get the single tail. So 16. Okay, and then here. So 16. Okay, now if you guys want to, use, you guys can use the Excel to do this too, right? So you don't have to use this rule if you are freaking out and you're like, I don't know how to do this. Let's do it this way. Okay, so it's a normal distribution, right? That's what they say. It's a normal distribution, normal random variable. Mean is 69, standard deviation is 3. So this is what you would do. Norm.dist my x, so the probability I want to find area around is greater than 72 inches tall, so it's 72. My mean then is 69, and standard deviation is 3, and it's always cumulative. Now be careful, I want to find the area to the right. Excel always default finds the area to the left, so I have to do 1 minus. And look at this, 15%. Well, it's closest to 16%, right? So then your answer would be 16%. So just go to the next whole percent. All right, so that would be my answer. Okay, now you have to use Excel for this part. What is the probability of normal random variable taking on a value less than 1.2 standard deviations below the mean? I mean, you can do it by hand, but why? It would be too annoying. So let's do it. So here, now it gives us a z-score, right? Because if we're talking about values that are a certain number of standard deviations below the mean, we're talking about z-scores. That's why when you see probability of z is less than negative 1.24, it's this, probability that z is less than negative 1.24. Well, why is it negative? Because remember, a z-score tells you how many standard deviations, it counts how many standard deviations you are from the mean. But if you're below the mean, then that means that you go to the left, so it's negative. Right? So we have negative here because it's below the mean. If it's above the mean, it's positive. Okay, so let's find this probability. So this is just norm. Now if it's a z-score, you can use .s.dist, but let's, just in case you like to just use norm.dist, it's okay. So click, my x is just the dummy variable. I want to find the area around, so the negative 1.24. But because it is standardized, so because it is a z-score, my mean is always 0, my standard deviation is always 1. And there you go, about 10%. So I'd copy this guy over, throw him in here, round to 4 places. So 1, 2, 3, 4. So it'll be 5. So I cut it off at 5. Check answer. And there we go. Okay. So what is the probability a normal random variable to take a value greater than z is equal to negative? Okay, so change this. Now just go in here. It's still the same thing. Just change it to negative 0.53, I believe, was the number. Yeah, greater than that. But it's greater, right? So it's going to be to the right. So greater than negative 0.53. So it'll be 1 minus this. And there we go, 70%. So to 4 decimal places again, it's 70.19%. Okay. Alright, oh, this is a long one. The probability is 67% that a randomly chosen adult male's height will be less than how many inches? Okay, so we want 67% to the left because it's less than, right? So 67% to the left, we have this. The probability that x is less than what? We don't know what is, but we do know that it's equal to 0.67%, right? 67. Okay, so to find the what, so let's just call it A. So to find my A, so this value, it's just going to be this. So the area is to the left. So what I'm going to do is when you're given a probability and want to find the data value, it's inverse. So norm.inverse. So click on my probability. And then you also need your mean and your standard deviation. So now I have to go back up. Remember the mean was 69, standard deviation is 3. Because we're not doing a sample, we're dealing with population. So 69, 3. And there you go. So 70.32 approximately. I think, what does it want to nearest tenth? So then it's just 70.3. And there you go. So that's how you do the basic probability one, like with standard deviation rule, and when you're dealing with just parameters. But remember, it changes when we're dealing with samples, right? So samples it starts getting a little more interesting. Okay, but let's go right to number. Oh, actually here too, if you're trying to just find a z-score, because there might be a problem like this on the final, possibly, I don't know. But if you're trying to get, like, let's say you have the x value, or let's say you have mean, you have standard deviation, and you have your x value. So let's say it's 67, and let's say your standard deviation is 4.5, and your mean is 78. Okay, you want to find the z-score, so find the z-score of 67. Okay, so the way you do this, standardize. So equals standardize will get you your z-score. Click on this guy, your mean, and your standard deviation. So there we go. So minus 2.444444 repeating, right? So that's how we find my z-score. Now if it is a sample, so this is only if it's population, but if you have a sample, so that means you have a n. If your n is 30 or whatever, let's just say 100, then because you have a sample, the z-score is going to change slightly, right? Because your standard deviation changes. Remember, based on central limit theorem, your central limit theorem kicks in. So this means that you have to do your population standard deviation divided by n. So in here you would just do, where's my standard deviation? Well, right there. So I divide it by n. So yeah, right? So then that would be kind of the same, I guess. But that's what it would be. So it looks, whoa, looks very, very different, right? Whoa, it's a big, big z-score. Okay, so that's how you would do these. Oh, oops, square root of n. Sorry, it's not divided by n. It's the square root of n, right? Oh crap, Microsoft. Oh no, is it happening again? Okay, whatever. I don't know why it's been acting up. It has not been acting up this bad, but whatever. That we don't even need to do that for this problem. Okay, let's go to now our parameters. So 39. So here we go. So U.S. males 20 years with 995 pounds, with standard deviation of 47 pounds, and distribution is skewed to the right. What is the probability the average weight of a random sample of 100 U.S. adults is less than 187.5? So look at this. So right away, we have this. We have central limit theorem, right? Okay, this is a weird place to open this. Whatever. So here we have, we want to find the probability that x bar is less than 187.5. So with our population standard deviation of 47, but look, we have a sample of 100 people. So we have, throw in all of your data here. So we have our mu, which is our population mean. We have sigma, which is our pop standard deviation. Then we have our n. So then we have to get our sample standard deviation, because we are having a sample here. So by central limit theorem, we have to have this. So my mu is just 195.5, so 195.5. My population standard deviation is 47. My N, well, that was the sample of 100 adult males. And then my sample standard deviation is, you take your standard deviation before, divide by the square root of your sample size, right? Okay, so 4.7. So we want to find a probability here. So my probability x is less than 187.5. So probability x is less than 187.5. Okay, so since this is a normal distribution, the cumulative part's always going to be 1. So just remember that. So norm, so we want to find probability less than, it's norm dot dist. Throw in my x. So my x is the value, the 187.5. So 187.5. My mean is the population mean. That's my best point estimate for my sample mean. Then your standard deviation is not the population standard deviation because we took out a sample, so it's this 4.7. And then it is always cumulative. So there we go. It's about right around 4%. So that is your solution. So there are 4 places. So that'd be 1, 2, 3, 4. So 6 is before it, so it rounds up to 4. Okay, and there we go. All right, so now we're looking at the parameters. So remember what the parameters are? The parameters are your population values. So this mu means your population mean. So my population mean was the 195.5. So 195.5. Now my mu of x, this is asking for your best point estimate. Remember, your best point estimate, though, is just what you have. The only thing we're given is my population mean, right? We're not given my sample mean. So then it's just going to be the same thing, 195.5. It's the only thing we're given. Then it asks for my population standard deviation, which is 47. Then it asks for the sample standard deviation. So if you ever see sigma sub x, now a lot of times for our sample standard deviation we just use s, like for later. But for here, when you see sigma sub x bar, this means your best point estimate for your sample standard deviation. So this is your 47 divided by the square root of your sample size, right? And n's 100, so we go back here, it's just our 4.7. So be very careful when you see that you do that correctly. Okay, and there we go. So now what is the probability that the weight of a sample of 50 US adults is between 172 and 186? All right, so now our sample changed to 50. So there, so make sure you do that. And look, because I was calling up everything in Excel, I get these guys for free, right? So my sample standard deviation will change based on that. So now it's 50, and I want to find the probability between. So find the probability between, there's a special way to do this. This is probability that x is between 172 and 186. So 172, x, and 186. Okay, so remember, finding the probability in between, so find probability between two guys is equal to probability larger prob minus smaller prob. So the two, you find two probabilities, so you find the area to the left of 172, area to the left of 186, then you take the larger one, subtract the smaller one, and you got it. So here we go. So let's find probability to the left of 172, then probability to the left, 186. Okay, find these guys. So this will just be a norm.dist, right? And to the left is easy. Our x is 172. What's the number we're going to find the probability around. The x is just the dummy variable. My mean is mu. Then my standard deviation is my sample standard deviation, and it's cumulative. Okay, so do the same thing again, norm.dist, but this time now it's 186. 186. My mean is still the 195.5. My standard deviation is still the sample standard deviation, and it's still cumulative. And if you see this, this just means that the number is, because remember before I used this for the fractions, so let's just change the format. If you see this, it means that the numbers are too large, right? So that means that it's too large for me to show you. So what you have to do, if you see this, it either start making this larger, and then you're like, oh crap, it's still in a fraction. So right click, go to Format Cells, and change it back just to general. Okay, and there we go. It's in a nice little form again. Okay, so this one's the bigger one, right? 7-ish%, and this guy's not even a full percent, not even close to a full percent. So you take the larger one minus the smaller, so big minus small, and this is the probability. So go over here and they say 4 places. So it'd be 1, 2, 3, 4. This is 3, and we kill the rest. There we go. So that's how you do the problem. So not too hard, right? All right, so we're getting close here. So 42. I've got just a few more problems for this first part, and then I'll do the second part. So 42 is the next problem I'm doing. Thank goodness it's only one part problem. So here, the red blood cells count of women are normally distributed with a mean of blah, 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 standard deviation of blah, blah, blah. Find the probability that a randomly selected woman has a red blood cell that is less than 4.2. So here it's just a randomly selected woman. So we're not taking a sample out, so we're just using the population data. So kill this. All right. So now, my n, well, I mean, if you want to, you can even think about n's just 1. But I'm not going to do that because it's weird. So let's do my mean of 4.577. So 4.577. My population standard deviation, because remember, this standard deviation doesn't flat out throw it in your face. It doesn't say, hey, I'm the population standard deviation, but it does say the standard deviation goes with this mean. Well, what was this mean? This was the mean of all the blood cell counts of all women, right? So this is the population mean, then that means this is the population standard deviation. So 0.3 junk, 382. 382. Okay? So that's it. So the probability that a randomly selected woman has a red blood cell count that is less than 4.2. So probability that X is less than 4.2. Okay? So here we go. So it's norm.dist. Here's your X value is 4.2, right? That's the probability you want to find around. Your mean is 4.7. Standard deviation is this one. Use the population because our sample size is 1, so we're not taking a sample out. And then cumulative, it's always 1. All right, and then the probability was lower than 4.2, so this is it. Copy this guy over, throw him in, and 4 places. 1, 2, 3, 4. Okay, and then don't round up. Okay, so check answer. And there we go. Okay, so now let's go on to question 47. So this is, now we're going to talk about confidence intervals. So this will be something you guys should pay attention to because this was right after spring break, so that might be why the test scores were, you know, not the absolute best out of all the tests. But just make sure you guys pay attention to this part because this is the tougher part, right? So this is the inference where things start getting kind of weird. So let's check this out. So the amount of money that a family spends on a night out and dinner in a certain city has a standard deviation of the population standard deviation, 22.09. If a simple random sample of 100 families is found to have a sample mean amount, x bar, blah, 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 estimate the population mean with 90% confidence. So remember, the confidence interval tells you with the given confidence. So with 90% confidence, whatever interval we get, which is based on my x bar, whatever interval I get has a 90%, and we have 90% confidence that our true population proportion, population mean, is within that interval. So this is what we're doing. Okay, so first off, I have my x bar. I have my pop standard deviation. I will need my sample. Actually, yeah, sample standard deviation. So I need my sample size, so just n. Then let's see, what else do I need? My population standard deviation, x bar, my sample size 100, confidence level. So confidence level 0.9. And then you can find your alpha and everything if you want to, but for these problems, only the first problem was the one that I noticed didn't really give it to you, but they usually always give you the z-score. So your special z-score, and they give it to us so we don't have to worry about finding it. So here, let's put in all of our information we have. My x bar is 55.39. So 55.39. Now remember, x bar is equal to sample mean. Mu equals population mean. So just remember that Greek letters are usually always your parameters, and then your like normal US or alphabet characters are English alphabet. Yeah, they're usually always the sample or the statistics. Okay. Oh, didn't like me doing that. There we go. All right, population standard deviation. It was given to us. It was 22.09. Okay, and then my n was, we were looking at 100 families, right? So that's my n. Now my z they give me is 1.645. 1.645. All right. So there we go. So now we can find our margin of error m, right? So this is my margin of error. So all it is, remember, it's your z times your sample standard deviation. So it's z times your population standard deviation divided by the square root of your n. Of course, when we do two population proportions and so on, it gets kind of hectic, right? It's a huge formula, but for one, it's easy. So there we go. That's my margin of error. Now I got to find my lower and my upper. So click on your x bar, subtract your m for the lower, then click on your x bar, add your m to get the upper. Okay, so let's throw these guys in there. Now please remember too, no matter what they're saying, even if you're doing this and they say it's wrong when you put it in this way, the format for a confidence interval is in interval notation. So interval notation says you're putting the smaller number first, then the larger. So we put in our smaller one, right, the 51, and we're doing it to the 100th, so this is 6. Okay, and then do the same thing. Now the upper, so the higher number goes in the second slot. Okay, so we're still doing 100th, so it's 59.023, so it just becomes 0.02. Okay, there you go. So we got it right. So 47 and 48. So another one. Okay, so wait, was there not a confidence interval for P? Guess there wasn't. Huh. Okay, but it's still the same process. It's still your special z-score times your sample standard deviation for you know, the value. So here we go. Let's do this. So 48. Well, actually, no, you guys should be able to do 48 now, because I mean, 47 is like the exact same as 48. So you guys do 48 on your own. But here, instead of doing 48, I'll do these guys. So which confidence interval will offer the most precise estimation of mu? So remember, look at this. This is a, wait, let me fix this really fast. So this is norm.s.inverse. So don't worry so much about this part. There'll be 1 minus, oh, I didn't do alpha, so it'd be 1 minus, again, divided by 2. Okay, so here we go, 1.645. Okay, so look at this, right? So this is, so with a 90% CL, the confidence level, I get my lower is 51.75 approximately, and so this is my lower, and then upper is 59.02. Okay, but let's look at 95% and let's see how it changes. So I need my lower, oh, lol, lower and upper. So for a 95%, oops, so 95% CL, let's do this. So I put here, now I do 0, 0.09, oh, it's 95, so 95%. Okay, look at this. Look what happened to my interval. It got larger, right? Ah, geez, it's actually not. Let's do 99.99.7, so it's a little more clear. Ah, there we go. So this is a 99.7% confidence level. Look at this. Now my lower is 48.83, and then my upper is 61.95. So this is, look at this. So when I increase the confidence levels, when I increase my confidence, the range of numbers gets larger. So that means I have a greater chance of having my mean in there, right? My population mean. But what's the problem? Well, if confidence level increases, this means that the numbers, the possible values that I have for my population mean, there's a lot more numbers to choose from. So in other words, the accuracy decreases. So as your confidence level increases, your accuracy decreases, right? And then, of course, the exact opposite for the other one. But, of course, it also, as confidence level increases, chance to contain population mean increases, right? So we have that, at least. So that's why you would increase your confidence levels, because you want to have a better chance to get your population mean in there. But if you increase your confidence level, your accuracy decreases. Now, accuracy, I'm using the term accuracy, but that just means precise, right? So precision. So I'll just say precision. So that way the keywords are the same. So precision decreases. So in other words, which confidence interval will provide the most precise, so the most precise estimation of mu? Well, the smallest confidence. So because we have a smaller range of values to choose from, so we have a greater chance of mu not being in there, but we have more precision. So 90%, so the smallest one, right? That is the correct answer. But now it says which interval provides the most amount of confidence but the least amount of precision. Look what I said here. If your confidence level increases, precision decreases. But what happens to the chance to contain population? It increases. So then if we want the one that's we're most sure will include our population mean, but that happens to come with a heavy price with not as much precision, it'd be the highest confidence level. Okay, and there we go. So problem 53. And this is another good problem too. So when using confidence intervals to estimate a population mean mu, in what ways can we realistically decrease the margin of error? Okay, this is saying in what ways can we get smaller values for m? So let's look at this. So look at our formula for m. So remember, the margin of error m is equal to my z-score, right? So this z times, so the z times my, let's see, it's standard deviation divided by my sample size n. Okay, so what ways can we make m smaller? Well, if we get z to be smaller, that would help, right? But how do we get z? Well, that's with my confidence level. But then, what's the main thing? Well, if we make n larger, that will make this fraction smaller, right? So if my standard deviation is 1 and my n is 2, if let's say I take 3, well, 1/3 is smaller than 1/2. So the best way to make my margin of error smaller is to increase my sample size. So if I increase my sample size, that's definitely one way. So now what else? What else will make m smaller? Well, look at this. So my margin of error here is 6.55. What happens if I make my confidence 0.9? Ooh, my z got smaller, but look what happened to my margin of error as well. It also got smaller. So changing your confidence level, making your confidence level smaller or decreasing it will also help. So decrease your level of confidence. Okay, and I believe that these are the only two because um, I don't think you cannot decrease a population standard deviation. Yes, it would help, but your population standard deviation is a parameter. It's a set value for your population. So you can't decrease it unless you are studying individuals and you go out and just destroy all the individuals and you're like, hey, I have 3 million humans and this is their population standard deviation. Oh, that's not good. Let's go out and blow up 500,000 of them. Then we can change our population standard deviation, right? That's not good. Blowing up people is never a good idea. So that's why it says realistically decrease the margin of error. So decreasing or increasing your population standard deviation is unrealistic unless you are fine with, breaking the law. So these would be my solution. Right? So only those two guys. Increasing sample size, right? Because it's easier just to take more people, right? If I say, hey, I have 99 people, I'll just go find one more. That's increasing your sample size. Decreasing the level of confidence. Might have a smaller chance of having our population mean in there, but it makes our margin of error smaller. Okay? And that's all I wanted to do for this first part of the video. So stay tuned and I will make the second part. All right, guys, thank you. And stay tuned for the second part.